Hello, everybody. I'd like to welcome you all to this month's webinar called Using Planetary Boundaries with LCA for Absolute Sustainability Assessment and Target Setting. We're so very pleased to have Bjorn with us today, who's a postdoc at Concordia University, Canada. Over the past decade, Anus has worked on linking the planetary boundaries framework with LCA to facilitate absolute environmental sustainability assessment. This allows researchers and practitioners to widen the focus from whether something is better for the environment or whether it's good enough for the environment. Likewise, an absolute perspective can be used to derive science-based targets for future environmental performance of companies, cities, technologies, etc. ANLOS's current research evaluates the integrity of science-based and net zero targets for greenhouse gas emissions set by large companies. During his presentation, you may ask questions via the Q&A. After this presentation, one of our EarthShift Global's analysts located in Mexico, Mariano Ortega, will ask those questions for you to him. Welcome, Anus. Take it away.
Thank you very much, Holly. You can all hear me, right?
Yes.
That's great. All right. Well, thank you for the presentation. I'm very excited to be here. So first of all, who am I? Well, this is a picture from before my pandemic hair, but I have a master's in environmental engineering from the Technical University of Denmark, where I also did my PhD. And since then, I moved to Montreal, where I did a postdoctoral fellowship at Polytechnique Montreal with the CIREC group. And there I was focusing on life cycle assessment method development, basically integrating planetary boundaries in life cycle assessment, which is what I'll talk about today. Now I'm still doing a postdoc, but I moved a few kilometers down from the mountains. Now I'm at Concordia University, and I have been affiliated with the John Molson School of Business and also Department of Geography. And so currently I'm focusing not on developing methods, but on studying the use of methods by companies for setting science-based targets and related assessments. And so I'll go over a few points in this presentation. First, why I think we need a paradigm shift in life cycle assessment. Then I'll go into some of the more technical elements of that paradigm shift and how LCA and planetary boundaries can be linked in practice. I'll then give some examples of company applications and shortly discuss future trends in the end. So first of all, why is it that we need a paradigm shift, according to me? So if you consider pretty much no matter what product or service you consider, the impact per product or per service has decreased over time. And so that's, good news. And of course, we'd like to think, at least in the lifecycle community, that we have helped make that happen by applying lifecycle assessment, by identifying hotspots for improvements, and by trying to avoid burden shifts across lifecycle stages, across impact categories. But it's not all good and well, because the state of the environment is kind of in trouble. We see here a selection of different state indicators. So for example, concentration of CO2 in the atmosphere and ocean acidification, nitrogen to coastal zones. And pretty much no matter what you look at, over the past 200-300 years, we've seen a worsening in the state of the environment, at least globally. And especially since the 1950s, there's been a heavy worsening. And so this is sort of driven by two factors, you could say, when you sort of cut down to basics. One is an increase in population on the planet, and the other is an increase in the total gross domestic product, so the total economic activity. That's also another way of saying it, that is that over time there has been a vast increase in the number of products and services delivered to man and women. And of course, we should also remember that there are many people in the world that are not receiving enough products and services. And then there are people that are receiving more than they perhaps need. So there's inequality in the picture as well. And because the number of products and services delivered tends to increase over time, it means that better is not necessarily good enough. It's kind of like if you look at how much you need to improve the environmental performance of products, it's always going to be a moving target, at least if we continue growing the number of products and services that are delivered. So what might be the elements of a paradigm shift? So I would argue that there are sort of three basic elements, and I'll present them one by one. So the first one, or ideas we could call them, the first idea is that we are constrained as a species by carrying capacities of the environment. And that's actually not a very new idea. We can trace it back at least 300 years to a thesis written by Hans Carl von Carlowitz. He was an accountant that worked for the mining industry in Germany. And he was basically trying to point out by this book that it's a problem that we have to travel further and further to cut down the trees that we need to stabilize the tunnels in the mines. For every new mine we build, we need to transport further and further away to find trees and to take them back. So he's saying at some point this is not going to be sustainable. I don't think he used that term, but that's essentially what he was saying. So he was pointing out that there are certain limits to what you can take from nature while having a sustainable economy. And today that kind of line of thinking, I think, is mostly symbolized, or it has materialized mostly in the planetary boundaries concept, which I imagine most of you are familiar with, but I'll also explain it a bit further later in my presentation. And so the premise of, before going into the technicalities of the planetary boundaries framework, I want to explain that the premise is that a stable environment is not a given. Even though since the last ice age, which is around 12,000 years ago, we have sort of become accustomed with an environment that is relatively stable, with the sea levels that are relatively stable and atmospheric content and temperatures that are relatively stable. But it doesn't mean that it has always been like that. So if we go back, this is a chart showing temperatures, how they deviate from today's level over the last 100,000 years. And you see prior to the end of the last ice age, which is what we call the Holocene, it has been there's been quite some instability. And of course, this is a long time scale, it's geological, so it doesn't mean that you wake up and one morning the ocean is like 10 meters higher than the day before, but it's still quite dramatic changes compared to the state of the environment as we're used to today. And what you can see also with the arrows that are linking to some text in the bottom of the chart, you can see kind of different important moments in the history of mankind, ranging from the first migrations of fully modern humans out of Africa. And so what you see is that in the Holocene, the red circle, that's where agriculture began on several different continents. And it's also where the so-called great European civilizations emerged. And so the authors of the proponents of the planetary boundaries concept, they will argue that it's not a coincidence, that we need a stable environment in order to have, let's say, a modern civilization development. And so another premise is that what caused, sorry, I should just go back here, because what caused this instability that we've seen over the last 100,000 years, I think it's not completely agreed upon by scientists, but part of it is geological cycles, and also cycles related to how the planet is orbiting the sun. And so this is something that causes cycles in Earth's climate. But in addition to these kind of natural changes that are happening over long time horizons, humans at this point in time, we have kind of become equivalent to a geological force by the way that we can manipulate landscapes and chemistry in the atmosphere and oceans, etc. And so given that in the past, geological forces have created instability in the Earth system, it's reasonable to assume that humans now have the power, whether we want to or not, to cause such instabilities as well. And so that's like the background, the backdrop of the planetary boundaries concept. And the concept itself, it's like a framework composed of 9 what we can call impact categories, because that's the term we like to use in LCA. And each of those has a suggested boundary for how much global impact the Earth can tolerate, let's say. And so the space between the natural background level and the boundary is what they call the safe operating space of humanity. And that's comparable to the concept of carrying capacity. And the derivation of these boundaries is based on a combination of threshold theories and resilience theories. And so the idea of thresholds is that in many ways, the environment reacts in a nonlinear way to increase the human pressure. In the beginning, there may be some sort of absorption capacities mechanisms that can counteract the impact of the pressure. So we will not see much change in the state of the environment. But after a while, this kind of capacity to express pressure has been depleted or diminished. And so that's when you can see a change happening fairly fast in the environment. And there are countless examples of that. For example, the eutrophication of lakes. Another thing to point out is that this is not an exact descriptive science to predict where these boundaries are located. And so in the framework, there's a kind of uncertainty built in. So there's a green space, and then there's a yellow space that might be too much, but we are not sure. And then there's a red space where we are pretty sure that it's too much. But the fact that we are in the red space also doesn't mean that we have necessarily already caused the Earth to shift into an unstable state. It just means the longer we stay in the red state, the higher the risk is that we are actually pushing the Earth out of the stability that it has been in until now, at least over the last 12,000 years. And so what you can see on the chart to the right is that according to these researchers, we are in the red when it comes to biogeochemical flows. So that's emissions of phosphorus and nitrogen. And we're also in the red when it comes to one of the measures of biosphere integrity, which is genetic diversity. That means we're basically killing species at a rate that is too high. And we are in the yellow for a bunch of other things: climate change, well, actually only 2 other things, climate change and land system change. So the second idea, in addition to carrying capacity or planetary boundaries, is that we need to find a way to divide this safe operating space, SOS, between different actors in society. And so this is something that has already been discussed for decades within the international climate change negotiations, where there's this idea that if you can quantify a global remaining carbon budget that is allowed before we reach 1.5 degrees or maybe 2 degrees, well, then we can think about that as a sort of global resource that we need to distribute in a fair way between nations. But the same line of thinking could really be applied to organizations, individual humans, and so on. And there are different principles for how to divide a scarce resource in a fair way. And I'll get into that later in the presentation. The third idea is then basically just a consequence of the first 2 ideas, which is that whatever you are assessing, whether it's a company, a city, a product, you can compare its impact to, well, you can compare it to the entire safe operating space, but it's more meaningful to compare it to the allocated or assigned share of the safe operating space to your product and to your whatever you're studying. And then the absolute sustainability assessment is then simply saying that if the impact is equal to or below the assigned share, well, then your system is sustainable, at least for that specific impact category. But if the impact is higher, then then the thing you're studying is environmentally unsustainable. And then what you can do is you can set targets for how much you need to reduce before you go below the ratio again. So that's the basic idea of absolute environmental sustainability assessment. So how are LCA and planetary boundaries linked in practice? What you can see, and I'm sure many of you are quite familiar with the life cycle assessment framework and impact categories, you see there are quite some similarities between the impact categories. You have climate change and ozone depletion on both of them, and you have something related to nitrogen and phosphorus emissions, which in LCA it's kind of organized under eutrophication and acidification. But overall, there's a pretty good match between the types of pressures and impacts that are covered. So one way to make the links is to take the impact categories we have in LCA that we typically work with, the set of impact categories, and try to create a link to planetary boundaries. And that's something I did a while ago actually at my PhD. I proposed such a link via normalization factors. And so the idea would basically be to normalize not by per capita current impact, which is what normalization usually is in life cycle assessment, but to normalize per capita carrying capacity. And I have an example of that. So this was another study that I was not involved in, but also by researchers in Denmark. And so they studied a house in an absolute sustainability assessment. The functional unit is a typical Danish single-family dwelling with a net floor area of 128 square meters and an estimated service life of 50 years. So the first thing they did, the researchers, was to assign a share of the carrying capacity of individual impact categories to the house. And so the first step was to apply an equal per capita principle. So that means that you go from what is allowed globally to what each person on the planet can impact by simply dividing by the number of people on the planet. So that's the first step. The second step to go from this per capita allocation to the house was to look at final consumption expenditure. So what is the share of a typical person's expenditure that is spent on cost related to having a house? So that was how they did the allocation or the cutting of the cake in this example. And what they found, I'm not going to go into details with the assessment, but what they basically found was that for 4 out of the 12 or so impact categories, the impacts were too high. And that was for land use when it comes to soil erosion, it was for climate change, and it was for freshwater eutrophication. In those cases, they found impacts being up to 10 times higher than what they should be, at least in the standard scenario. Then they ran some other scenarios with different parameters to check the sensitivity of their results. This is why you see 8 columns and not 1. But basically, overall, it was those 3 impact categories where the problems turned out to be. And so for climate change, the fact that you are overshooting by something like a factor 10, and the same for land use change, means that you essentially need to improve the environmental performance of your system by a factor 10 to claim to be environmentally sustainable with respect to this sharing approach or allocation approach. Next, so now I spoke about one way of linking the framework, which is to start with the LCA impact categories and try to bridge planetary boundaries. The other way of doing it is to start with the planetary boundaries and try to link with the life cycle inventory by developing characterization factors. And one of my colleagues, Morten Ryberg, and colleagues from DTU, Denmark, they developed such an approach a few years ago, which is basically a set of characterization factors. So instead of using the characterization factors that we use to go from inventory to classical LCA impact categories, we completely abandon those, and we use a new set of characterization factors that takes you from inventory to the exact categories in planetary boundaries framework. One sort of weakness of this approach is that you are not able to cover human health impacts or abiotic or mineral resource use. And that's simply because the nature of the planetary boundaries framework doesn't really care about impacts on humans, either direct on health impacts or sort of impacts that happens due to resource scarcity. All that the planetary boundaries framework care about is to avoid causing the Earth system to become unstable. And the Earth system doesn't care about the health of the humans living on it, at least not directly. So that's why. So there are some impact categories that we typically cover in LCA that we cannot cover if we want to be completely loyal to the categories in the planetary boundaries framework. And to give you one example of a study that came out a couple of years ago that used this approach, it was a very interesting paper with the title "Powering Sustainable Development Within Planetary Boundaries." And so the starting point was the boundaries themselves. And then they did, and I should say it was for the US energy system in the year 2030. So first they had the boundaries, so the safe orbit gate space, and then they did a national downscaling by population. So again, it's kind of like the other example where you use a per capita approach to say, in this case, how much can a nation take up of the total allowable impact. So that gives you the US share of planetary boundaries. After that, they used gross value added to further downscale to the energy sector. So that's basically out of the entire GDP of the US, what is the contribution of the energy sector to the gross domestic product of the US? And that proportion was used to do the last downscaling step. And so basically that after they had those downscaled planetary boundaries or safe operating space, whatever you call it, they kind of fit those as constraints into an energy systems model. And in addition to that, they fit a life cycle inventory of different electricity generation technologies. And they coupled that with the characterization factors of that study I just presented, the Wullback study, so that they had the sort of impact per unit of electricity generated for different technologies. And so they fed that into this energy systems model, and they asked it to kind of solve the system. So, how can the energy system we have today be changed in the year 2030 so that we are within the allocated planetary boundaries to the US electricity? And what they found was, so first they ran a business as usual scenario where they didn't have the planetary boundary constraints. They just the US energy system is basically developing as it would do according to markets and policies in place and stuff. And so in that scenario, what you see is that to the top right, this little pie chart is that the electricity mix would be mainly composed of coal, natural gas, and nuclear, and quite some hydropower, and very little anything else. So what you see in the big chart to the left is that if that is the case, then you would basically overshoot the electricity system would overshoot its allocated boundaries for 5 of the 9 impact categories. So, well, technically 4, because there are 2 different indicators for climate change. There's the atmospheric concentration of CO2 and the energy imbalance. So for climate change, it would overshoot. It would also overshoot for ocean acidification, which is highly related to climate change because CO2 emissions causes ocean acidification. But it will also overshoot for nitrogen emissions and for freshwater use. And you can see that it would overshoot by quite a lot, like by more than a factor 1,000 for some impact categories. So after that, they ran the model as I just explained with the planetary boundaries constraints. And they found that there was basically no solution in the model for where all allocated planetary boundaries was respected. But the solution they found with the least exceedance of boundaries was this one. And in this case, it's only the nitrogen emissions that are too high, that are higher than they should be. And all the other emissions and resource uses stay within the allocated boundaries. And you see that it's a very different electricity system. It's a system that's mainly composed of wind, onshore and offshore. and natural gas with carbon sequestration and storage. So this is where you burn natural gas, but instead of letting the CO2 go out to the atmosphere, you capture the CO2 and pump it underground before it's emitted. Right, and yeah, I think that's what I want to say about that. There's much more detail to look at in this study, and I encourage you to look at it later if you're more interested. And now, so the two examples I've just shown are sort of academic. You know, they are published in academic journals. It's very interesting as a researcher to make such studies and to read studies of other researchers, but it doesn't necessarily mean that these studies inspire use in real company settings. So now I'm going to show some applications that are done by companies that has an absolute sustainability assessment, let's say, element to them. So the first example I have is science-based targets. So this is the Science-Based Targets Initiative is basically a collaboration between 4 big NGO or non-for-profit consultancies that was established in 2015, right around the Paris Agreement. And so they define science-based targets as being in line with what the latest climate science says is necessary to meet the goals of the Paris Agreement, which is to limit global warming to well below 2 degrees, aiming to 1.5. So you see, it's the same logic. You are comparing the impacts of companies to a global limit. In this case, it's the 1.5 degree Paris Agreement goal, or the well below 2 degree goal. And then you need to find a way to sort of downscale that to emission pathways at the company level. And what we've seen is that the first couple of years, there was a little bit of a limited uptake by companies, but then especially around 2019, we started seeing more and more companies signing up. This chart is showing on the left side with the bars, that's the amount of companies that signed up every month. And what you have on the right side, and that relates to the curves, that is the cumulative number of companies. So you can see today there are more than 1,000 companies that have signed up over the last 5 years. And what you can also see is that today it's more and more common for companies to sign up according to the 1.5 degree goal. So that means that their emission targets are aligned with the 1.5 degree goal rather than the somewhat less ambitious 2 degree goal. So over time, the ambition of the companies setting science-based target has increased. The companies that set science-based targets, they tend to be headquartered in North America and Europe, and quite a lot in Japan as well. But of course, many companies are multinational, so they will have operations in many other countries than where their headquarters is located. We also see that this is an overview of the sectors, the industry sectors that the companies with science-based targets belong to. And what you see is that there's a lot of consumer goods like brands, and also services, professional services and other services such as banks, consultancies, different kind of service providers. And there's a little bit less, it's less common for the very heavy sectors related to power and raw materials and chemicals to set targets. So currently, even though a lot of companies are setting targets, there's still a limited uptake in the sectors that really have the high emissions problem. So to give a couple of examples of companies that have science-based targets, one is Coca-Cola. So they are basically aiming to reduce their absolute scope 1, 2, and 3 emissions by 30% between 19 and 2030. And another example is Microsoft. So their target is phrased in a different way. They are aiming to source 100% renewable electricity through 2030. And then they, in addition to that, they also commit to reducing their scope 3 emissions intensity per unit of revenue by 30% between 17 and 30. And so just those two examples shows that there's quite science-based targets can be phrased in different ways and cover different things. So there are differences in the base year and the target year that companies choose, in the targeted reduction between the base year and target year, in the emission scope, whether both scope 1, 2, and 3, all scopes are covered, or if there's a focus on, let's say, only scope 1 and 2. Also, whether the target refers to absolute emission reductions or reductions in emissions intensity. And finally, and this is a little bit less visible, but there can be a difference in the underlying method that companies use to calculate their science-based targets, and the sharing principles, allocation principles that are embedded in those methods. And so here are like 4 examples of principles that often appear in the method. So one is grandfathering, there's cost optimization, there's physical production. So the more you aim to increase your production in the future, less you need to reduce in an absolute sense, and then convergence. And I don't have the time to really go into details with these principles, but you can look at the literature related to science-based targets if you're interested. The second example I want to give is more something that is starting up. It's not yet mainstream the way that science-based targets is becoming. So this is an initiative that is related to science-based targets initiative. Science-based targets initiative only related to climate change, but this initiative, which is called the Science-Based Targets Network, they have this project where they aim to develop a method, and they have been working on that for a couple of years. And they are saying that later this year, so in 2022, they will have an operational method developed. And the idea is to cover other types of impacts than climate change. And you see from that framework, it looks a little bit different than what we have in LCA, but they are basically considering 3 different environmental mediums, so land, freshwater, and ocean. And then they are considering the different drivers of impacts within those mediums. So that can be resource use, land, water, sea use, can be climate change, other pollution, and then invasive species. So the framework is a bit different than what we do in LCA, but they still very much build on life cycle thinking. And to give a bit more detail, they have this kind of 5-step framework that they have defined now, which is for a company to first assess, then interpret and prioritize, then measure and set target and disclose, and then act, and finally track. And yeah, there's a lot of detail here, but a couple of things worth highlighting is that they really emphasize location-specific assessments. So both in terms of the data of the specific locations where a company is operating, but also in terms of the carrying capacity of that location. Because you can imagine, for example, for freshwater use, it really depends what watershed you are in, what part of the world you are in, for how much water scarcity you are causing by taking, let's say, 1 cubic meter of water from stream. The other thing they also have an emphasis on is positive impacts. So, in life cycle assessment, we typically only consider negative impacts. So every time you emit an emission or use a resource, you have negative impacts associated with that. But here they are considering positive impacts, which can happen through restoration and regeneration of lands and transformation. I'm still not sure what that means exactly, but it's kind of at the landscape level that companies can do something to improve degraded lands, essentially. Right, so now we're sort of nearing the end of my presentation, and I'm going to speculate a bit here about future trends. And again, this is kind of speculation, so I'm not saying this is going to happen for sure. But I think one future trend is to see science-based targets for other impacts than climate change. It's clearly something that's gearing up. And yeah, also the fact that climate change, the fact that science-based targets for climate change have become so popular these days, I think will drive science-based targets for other impact categories, because companies will realize that there's a risk of burden shifting if you only focus on climate change when you try to reduce your emissions. You need to also consider what happens with land and water and biodiversity, etc. And I think as companies set science-based targets for climate change and beyond, I think the need for product level assessments will increase for companies to really figure out how they can, when they look at the portfolio of products, how they can sort of meet the science-based targets that they had for the organization as a whole. And I think maybe we will see more convergence of corporate environmental accounting and LCA than what we've seen to date. But there are a bunch of requirements that I haven't yet seen being met to facilitate product level assessments. One is to have support from software and databases. And so this both relates to, characterization factors, but it also relates to other things like the principles for sharing or allocating carrying capacities to individual actors, and the sort of the data that needs to feed into operationalizing these principles and equations, and also handling spatial and temporal differentiations. The two examples I showed you earlier, the one with the house and the one with the US electricity system, they both took a global perspective. So the impacts were calculated as kind of global average impacts, but we know that many carrying capacities are highly local. The example of water is a good one, but also related to acidification and different pressures on the land. So we need to get better at handling spatial and temporal differentiation. This is also a challenge in more classical LCA, by the way. And as I already said, we need to operationalize the principles for sharing or allocating safe operating space and the related data. There needs to be some sort of systematic development of these resources, I think. And finally, it's not enough to just operationalize and have data to allocate a safe operating space to an actor. You also need to understand what sharing principles are broadly considered fair in society. This is something I've seen very little research looking into. So some take-home messages. I think that Planetary-based LCA or absolute environmental sustainability assessment is needed. I don't think it will replace or should replace traditional relative life cycle assessment, but I think that it is needed as a complement. There's been a lot of method developments recently in this sphere, and we've seen a high company uptake of science-based targets for climate change. And I think that could maybe lead to a broader adoption of these methods that have been developed, but has so far not been applied so much outside academia. Finally, just a reminder or a disclaimer, let's say. So absolute sustainability assessment is not like a silver bullet that's supposed to solve sustainability forever and for everyone. It doesn't settle the discussion of what a sustainable society looks like or how we get there as a society. And most importantly, perhaps it doesn't replace government regulation. Because companies can do something voluntarily, it doesn't necessarily mean that we don't need governments to regulate them. All right. Thank you very much for listening, and I'm happy to take your questions. And you can also send me an email later if you want to have a more in-depth conversation.
Thank you, Anders. And I think that Mariana is going to unmute here in a moment and ask you some questions. I saw that there was a number of good questions rolling in.
Yeah, thank you, Sam. Thank you, Anders. So many questions, good questions. So the first one attendee comments, many LCAs are performed at product level. We know that. So how will we connect the results to interpret to the scale of the planetary boundaries? And I guess this question can go together with this next one. So what is the implication of the lack of global consensus on how to downscale the planetary boundaries to companies, products, etc.?
Thank you. So the first question, of course, we know these discussions that have taken place in international climate change negotiations around how we can share a global carbon budgets between nations, and that has already been quite complicated and more or less abandoned in favor of this national determined contributions, this kind of bottom-up approach to solving climate change by international policy. And so, of course, it gets even more tricky when you talk allocations not to nations, but to individual products. But it can be done in practice. There's nothing that prevents it from being done. I gave the example of the house. House is a product. It's a big product, but it's still a product. And so I gave the example of the kind of two-step allocation that has been done, where you first allocate the global allowable impacts to a single person, and afterwards you allocate, when considering all the different services and products that that person consumes, you need a way to sort of allocate between those, and that can be done in different ways. One of them being looking at the typical expenditure how much people spend on different categories of consumer goods. And of course, it's not the only way. Let's say it's a convenient way to demonstrate the approach as a researcher, because you have the data, but you could also argue that it's more relevant to look at what are the products and services that are really critical for human well-being. So let's say if a person was to cut his or her impacts by a factor 2 or 3, what things would you prioritize keeping and what things would you get rid of? That would perhaps be a more relevant way of allocating to products. But again, we don't have much data about that. At least I haven't seen any sort of solid studies on that. So that's my answer to the first question, is that in theory, you can definitely make the link from the product to what is required at the global scale. But of course, it gets tricky when you get into the technicalities about what principles should we use to allocate, and how do we get the data to feed into these allocation models. And I guess it relates to the second question on what are the implications of the lack of consensus related to this, what is a fair way to share. Well, we've seen that in the science-based, in the realm of corporate science-based targets for climate change, right now companies can choose between a couple of different methods when they set their science-based targets. And there has been some speculations that companies might choose a method that gives them the highest possible, the most benign allocation. I don't know if this is what happens in real life, because there's a bit of lack of transparency about how companies actually use the method that is behind their targets. But it's certainly a speculation that you could have that if you give actors the freedom to choose between different principles for allocating, many actors might, first try to calculate with this principle, then calculate with that and that, etc. And then they compare the results and say, okay, this is the good principle because it gives us the easiest target. That's a kind of cynical theory, but this is one of the risks of not having a consensus of what is a fair way to allocate between nations, between activities and actors. And so I don't know what the best way of solving that is. Is the best way to try to agree everyone what is a fair way to share? Or is it to sort of build a buffer into your system so that everyone should actually aim for a slightly harder target than what they initially calculate, just to account for this cherry picking effect? I'm not sure what the best approach is.
Thank you. Now, a bunch of questions that are very technical to the point. So is the time dimension incorporated? Coming back to the example of the house, it says there's embodied carbon to build the building, and the impact of this can be lowered by reducing the inputs, but the operation, the energy use can be very large over the life cycle of the building. So how or if is the time dimension incorporated?
That's a very good question. So some of the assessments that link planetary boundaries and LCA, they take a kind of steady state approach. So saying that each year the environment can sustain a certain amount of impact. Like this year it can sustain that much, the year after the same, etc., etc. So it's like a sustainable amount of impact that can be, in theory, maintained forever without causing the environment to degrade at an unacceptable level. And so when that is the approach you take, then you would ideally want your inventory to also be at an annual basis, so that you can compare the annual inventory to the annual allowable impact. But of course, that's not always what you have in a life cycle inventory. You don't always have that time information. And like the question was hinting, there can often be years or decades from the impacts happening upstream to the impacts happening downstream after the use of the products, could even be close to a century for a building. So that is definitely, and let's say it's a challenge that it kind of goes back to that what I mentioned on one of my slides, that we need software and databases that better take care of both spatial but also temporal resolution, let's say, or differentiation in your data. So yeah, the example that I gave with the house, I'm pretty sure they somehow, I have to go back and look at the data, but I think they somehow allocated the impacts from building the house, the embodied impacts, to say, I think they allocated those over the years of the expected lifetime of the house to get a kind of average annual impact. But of course, in reality, the impact is going to be not equal over years, but kind of up and down, right? So this is something we would need to be better at for operationalizing these assessments. And another, that was like half of my answer. The other half, and I'll try to make that briefer, is that when it comes to climate change specifically, one thing you maybe saw for science-based targets is that with science-based targets, the idea is not to have some sort of steady emission of CO2 and other greenhouse gases to the atmosphere that you can like maintain forever. Because CO2 is such a long-lived pollutant in the atmosphere, we know that warming kind of scales with cumulative emissions of CO2. And so as long as you are more than zero emissions globally, the Earth will technically keep warming. That's the sad truth. And so the steady state approach is not really so applicable to climate change. That's why with science-based targets, they base the allowable emissions on global emission scenarios that are like starting with today's level and then going down until it hits net zero around 2050. And so in that case, you also need these temporarily resolved inventories of emissions because it matters what year your emission happened, whether it's judged to be too high or low enough.
Thank you. In fact, I think maybe that touches upon these questions, this next question. What do you see as the main advantage of the science-based targets in LCA, and what is the main drawback?
I think the main advantage is that it gives decision makers a direction and a target. Because with usual LCA, which is something I like to call it relative sustainability assessments, because you always compare your product system to some sort of reference that's specific to your assessment. And so when decision makers see these results, of course, it's nice to know if what you're studying has a lower impact than something else. And it's nice to understand where in the life cycle you have low-hanging fruits for further reducing impacts. But it doesn't really inform you about where you need to go in a more strategic sense. Like, so, is it good enough? Is it fine? Should we just stop innovating? Or, and I think the absolute sustainability approach will give you that direction. It will tell you, no, the product is not sustainable today, but if you reduce by a factor 5, it will become so. At least with reference to these allocation principles that lie behind an assessment. And that kind of is maybe a segue to go to the disadvantage, because I think the disadvantage is that it's inevitable that you have this step where you need to allocate from what is allowed at the global scale to the thing you're studying. And that is always going to be subjective. It can never be done in a scientific, objective manner. And so you do need to deal with different perspectives of stakeholders, and probably you need to calculate a range of results rather than a single result that reflect different perspectives of what a fair way of sharing global resource is. And so that is, I think that's the main weakness, but it doesn't mean that it's in itself is a reason to not do these assessments.
Of course. And you noted that planetary boundaries are quite uncertain. So has this been considered, the uncertainty in any of the work to date? And what are your thoughts around how this could be considered?
Yeah, so actually, if I go back a few slides, I think I didn't mention that clearly enough. But for example, this example here, you see that they have what they call a safe zone, an uncertainty zone, and a high risk zone. So the colors green, yellow, red, which is part of that spider plot. And so they do consider that in the planetary boundaries framework, you have these three zones where one is safe, one is uncertain, and one is unsafe. And so the uncertain space, like the wider it is, the more uncertainty there is in the ED assessments of where the planetary boundary is located. And so that this uncertainty is quite directly communicated in the planetary boundaries framework, and it can also be taken into account in life cycle assessment that builds on planetary boundaries. So, in this case, I think all the impact categories are either uncertain or all the impact categories or the impacts, sorry, I should say, are either in this example definitely too high or definitely low enough. So you don't have an example of an impact that is in the zone of uncertainty, but that could have happened.
Thank you. Where we only have a few more minutes left, so I want to put together two questions that bring together like the global scale targets and a local or more product level one. So what is the difference between the planetary boundary for climate change and the Paris Agreement goal of limiting warming to 1.5 to 2 degrees? Because that's a big goal, right? And then wouldn't it be easier to achieve reductions by developing targets for product?
So for the last question, easier than what? Because we are developing, you mean easier than deriving targets based on global allowable impacts?
Such big scale.
Well, you can always develop a target for a product based on some nice round number, like we want to make it 10% better or 15% better in 5 years and 10 years, but you're never going to know if those targets, sure, those targets might lead to reductions in impact, but you will not really know if that reduction is good enough considering the global state of the environment. So it can be a good way to motivate reductions of impacts, to set targets that are not informed by global reduction needs, but you lose that link. You will never know if your target is ambitious enough, for example. That would be my answer to the second question. And the first question about the difference between the planetary boundary for climate change and the goal of the Paris Agreement. So the planetary boundary for climate change is actually more strict than the goal for the Paris Agreement, because the planetary boundary for climate change has already been exceeded by its state goal. So for CO2, the goal is to have a 350 ppm concentration in the atmosphere, and that concentration threshold was already exceeded, I think, around the year 1985 or 1990 or something like that. And today we're around, I think, 415 ppm or something like that. So that means to basically get below the planetary boundary for climate change again, we would essentially need negative emissions, net negative emissions. For the Paris Agreement, the goal 1.5 degrees is also highly ambitious, but it's still technically achievable. And we still have a little more emissions to emit globally before we will reach 1.5. So the planetary boundary for climate change is more strict, and maybe a reason for that is that it doesn't really take into account what's feasible from an economic or engineering or political perspective. So it's not something that has been reached in a negotiation between politicians. It's something that they considered, that the scientists that define the boundary, they considered the natural variability of CO2 in the atmosphere over thousands and thousands of years and use that as an indication of what is like, what human impacts on the atmospheric concentration of CO2 that kind of lies within the natural variability. So they saw that as an indication of what would be safe.
All right, thank you. Closing questions. How would you develop targets for a new company? And is there any software for supporting companies to implicate planetary boundaries in their environmental assessment?
I'm going to start with the last question. So there is a Science-Based Targets Initiative have developed tools for calculating science-based targets for climate change. But there's not yet a similar tool for doing it for other impact categories, at least not that is very straightforward and user-friendly. There has been some attempts in LCA software, I think CIMA Pro and maybe OpenLCA, to integrate those characterization factors that has been developed specifically for planetary boundaries by Morten Ryberg and my other Danish colleagues. And so that allows you to basically calculate the impacts of a product system or company in the indicators used in the planetary boundaries framework. But it doesn't allow you to do the allocation. So the allocation to figure out if the impact is low enough or too high, you also need to go through that allocation step. And from my knowledge, that step is something that is not really integrated in life cycle assessment software or databases, at least not for the time being. But there's some momentum outside the LCA community. For example, I showed you the Science-Based Target Network initiative, and I think they will probably also develop tools later this year for calculating science-based targets at the organizational level for other impacts on climate change. So that's something that's going to be very interesting to follow. But for now, there's still a bunch of things that needs to happen in the LCA community, like database and integration in software, for this to really be straightforward to do an assessment. Yeah, I think that answered those questions.
Thank you so much, Hannes. There are a few more questions came in, very specific about the location, about choosing an impact category, and about your thoughts on a recent piece by Professor Guinet, published in the Journal of Industrial Ecology.
Right. Yeah.
So maybe you're very kind to answer them by mail.
Yeah, you're welcome to send me an email for sure. Please do that, and I'll make sure to get back to you. And just in case you didn't note it before, I'm just gonna go to the last slide with my email address, let it hover for a few seconds so you can write it down.
Thank you so much, Anders. We appreciate your time, and we hope to have you come back maybe for another panel sometime. And this is recorded, and we will post that once it's done. Thank you so much.
Thank you for the invitation, Holly, and thanks for engaging with the listeners, the audience, with the questions. It's been very interesting. Bye-bye.